Hi everyone, this is Keke, a research fellow from National University of Singapore. Today I present you my work, How Universal Polynomial Bases Enhance Spectral Graph Neural Networks, Heterophony over Smoothing and over Squashing. This work is collaborated with Professor Yu Guang, Professor Li Min, and Professor Pietro. Graph neural networks, or GNN, are well-known methods for its effectiveness in graph-related tasks. For example, consider a social graph where each node is associated with an attribute. When inputting this graph to GNN, it generates embeddings for all nodes for various downstream tasks. For example, link prediction, node classification, and recommendation. These embeddings are normally generated by message passing. For example, consider this brown node. It has 3 first-hop neighbors. And then the first layer aggregates messages from those first-hop neighbors. Similarly, for those first-hop neighbors, the second layer aggregates messages from their second-hop neighbors. This message passing paradigm is defined by propagation matrix, where propagation matrices are usually variants of Laplacian matrix. Given graph G, Laplacian matrix A is defined in equation 1, where I is the identity matrix, A is the adjacent matrix, and D is the corresponding degree matrix. Here is a Laplacian matrix example of the toy graph on the right corner. As we can see, the diagonal elements are all ones. For connecting nodes, the corresponding elements are defined by equation on the right side, which is 1 minus 1 over the square root of the product of their degrees if the two nodes are different. It is equal to 1 if the two nodes are the same. When applying Laplacian matrix on graph signal, it essentially conducts Fourier transform. To illustrate this, let's first look at Laplacian decomposition, where L is decomposed into U, gamma, and U transpose. Here U is the matrix of eigenvectors. Phi I is the ith eigenvector acting as the signal basis. Gamma is the diagonal matrix, where the diagonal elements are the corresponding eigenvalue, which are in the range of 0 to 2. The ith eigenvalue marks the frequency of the ith eigenvector basis. Here we have plotted the first 3 eigenvectors in this figure. As we can see, the eigenvectors associated with higher eigenvalue demonstrates more fluctuations, which is more ups and downs. That means has higher frequency. So when applying Laplace matrix on graph signal X, it performs Fourier transforms as follows. U transpose X is the graph Fourier transform. It projects the signal X into each of the directions defined by the corresponding eigenvector and returns X hat. Then X hat is either enhanced or suppressed by gamma matrix determined by the corresponding eigenvalue. Then, in the last step, it conducts inverse graph Fourier transform by multiplying X hat with U, and which converts X hat back into X. In real-world applications, we make gamma as a number function with parameter omega. So the resultant GNN can filter signals as we desire. However, performing the Laplacian decomposition requires a big O n squared time, which is impractical for the real-world datasets. So in the literature, we normally use the polynomial approximation techniques. Specifically, given integer k and propagation matrix P, the n-order Laplacian polynomial is approximated by the k-order polynomial. Here, propagation matrix P is usually the variance of Laplace matrix, such as L, I minus L over 2, etc. In existing works, there are several polynomials utilized. For example, monomial, Chebyshev polynomial, Bernstein polynomial, Jacobi polynomial, and orthogonal polynomial. Each of them has been utilized to develop polynomial filters. Here we give an example of Chebyshev polynomial. In Chebyshev polynomial, it first defined T0 and T1. Then the subsequent terms are defined recursively by using the previous two terms. Here X is working as an operator, for example, the operation matrix. Notice that the later terms is one order higher than the previous term. So we plot the first 5 terms in this figure. As we can see, the higher order of the polynomial, the more fluctuation the corresponding basis, i.e. with higher frequency. There are several limitations of existing polynomial. First, the lack of adaptability. To explain, polynomial basis is fixed without adapting to the homomorphic ratio H of graphs, where H is the probability of the connected two nodes from the same class. Here we have 2 examples, one in the homomorphic graph and one in the heteromorphic graph. We can see that on homomorphic graph, nodes from the same class are prone to connect to each other, where the themes are opposite on heteromorphic graphs. So it is critical to take the homomorphic ratio H into consideration when we conduct message passing. Second, the existing polynomial bases tend to converge, leading to the over-smoothing issue. The frequencies of the polynomial bases converge to that, the one represented by this red line. Similarly, in the spatial domain, the corresponding signal vectors converge gradually to this red signal vector. So the goal of our work is to optimize the message passing process to construct a universal polynomial basis, such that it provides adaptability to graphs with various homomorphic ratio H. We're trying to avoid the over-smoothing issue. Our goal is built on 3 insights. First, insight 1 proves that for a given graph with homomorphic ratio H, the frequency of the ideal filter signal is proportional to 1 minus H. Insight 2, we officially prove that the over-smoothing phenomenon surely occurs for most of the existing polynomial bases. Finally, insight 3 reveals a relationship between the angle of the signal bases and their frequency difference. Specifically, a larger angle tends to correspond to a greater frequency gap. Based on these 3 insights, our desired universal basis is designed as follows. First, insight 2 says basis vector in message passing converge. So intuitively, we fix the basis vector angle to theta. So the next question is, how large should we set the theta? Insight 3 here says basis angle related or proportional to frequency. Meanwhile, insight 1 says the frequency of ideal signal is proportional to 1 minus h. So we can simply set theta is proportional to 1 minus h and take 1 minus h as a factor times pi over 2. So our new basis is constructed as follows. Given the first basis vector u0, the second basis u1 is constructed by forming a theta angle with u0, where theta is equal to 1 minus h times pi over 2. Similarly, the third basis vector u2 forms a theta angle to both u1 and u0 at the same times. Essentially, whenever a new basis vector is introduced, it consistently forms an angle of theta with all the previous vectors. As such, we can optimize the existing polynomial basis by including our new basis using a parameter tau, where tau is in the range of 0 to 1. Consequently, we propose the novel universal basis, referred to as unibasis. Based on unibasis, our unit filter is constructed in equation 1 and equation 2. Specifically, equation 1 conducts signal filtering and generates the embedding zk, and then zk is fed into MLP and softmax for the final prediction. Next, we prove that our unit filter is able to address the oversmoothing issue. Specifically, the oversmoothing of generated embeddings on graph G is measured using Dirichlet energy. For each edge UV on graph G, we calculate the square of the true norm of the embeddings. Dirichlet is then obtained by averaging this value over all edges of G. So, oversmoothing occurs if this Dirichlet energy approaches 0 for sufficiently large K. And we prove that unit filter is able to address oversmoothing by showing that when K is approaching infinity, the Dirichlet energy of zk is equal to 1 minus tau of the Dirichlet energy of the input feature x. Oversquashing describes the phenomenon that a bottleneck occurs during the message passing. Consequently, a large number of messages is squeezed into a fixed length vector. Intuitively, it can be mitigated by simply adding more edges to the bottleneck connections. Formally, consider the embedding zk, node uv with distance k, and propagation matrix P, where zk is the embedding obtained by message passing within k hops. Then oversquashing occurs when the partial derivatives of du over xv is smaller or equal to a constant c times the propagation matrix P to the power of k of element uv. We prove that our unit filter mitigates oversquashing because we show that this partial derivative is independent of the propagation step k. In experiment, we test both homophony networks and heterophony networks. In each type, we included 3 different datasets, and this table gives the statistics of the 6 datasets. For baseline, we compare 11 polynomial filters and 9 model-based methods. This table presents the classification accuracy of our unit filter compared to 11 polynomial filters. The highest score are in bold, and the second highest score are underlined. As shown, unit filter achieves the highest accuracy score on the 5 out of 6 tested datasets, except on actor. In particular, on the squirrel dataset, unit filter achieves an accuracy of 67.4%, which is nearly 3% higher than the second one. This table presents the classification accuracy of our unit filter compared with the 9 optimized based model. As shown, unit filter achieves the highest accuracy scores on all 6 tested datasets. These facts demonstrate the clear advantage of UniFilter over the baseline. We also conduct an ablation study to verify the capability of UniFilter to detect the over-smoothing issue. These two figures illustrate the duration net evolves as we increase the propagation hop k. As shown, the duration net value stabilizes as k increases and are also proportional to the tau values. This observation aligns with our analysis. To address the issue of oversquashing, we create a synthetic dataset where the number of visited neighbors grows exponentially with each propagation hop. We then evaluate GCN and UniFilter on this synthetic dataset for load classification. This figure shows the accuracy trend of both GCN and UniFilter as the propagation k increases. As shown, UniFilter maintains a relatively stable performance compared to that of GCN. These results indicate that UniFilter effectively mitigates the oversquashing problem. That's all. Thank you.